I'm using a different thermodynamic property. What other thermodynamic property have you guys used in the past to tell if something is or is not spontaneous? Yep, you've used Gibbs, and you've used it in probably every class you've had, right? Except maybe Gen Chem 1. People who are in biochem, that's like 90% of it, right? Do you know what conditions you have to consider the Gibbs energy? With Gibbs, a lot of times you're considering constant what? Yeah. Yep, it's at a, usually, yeah, because you're thinking what equation? Yes. And yeah, that's at one given temperature. So most of the time, yeah, you're right, Shannon. It's where you're considering that. We're at one temperature, right? Okay. What is this thing? What is enthalpy? What is it at constant pressure? Yeah, it's the heat exchange with the surroundings. And this is what's happening to S of the system. So this is valid under constant what? Temperature and what else? Pressure. You use Gibbs when you have constant pressure systems. That's why we always talk about Gibbs, because we say, at constant pressure, we have pretty well controlled HVAC systems for labs. It's going to remain the same. We're going to move beyond just the general chemistry equation, and we're going to figure out, like, where does this equation come from, and what happens if we don't have a constant T? How can we move beyond that? We're also going to talk about the other situation, constant what? Yeah, volume, and that's where Helmholtz comes from. Okay, so the whole point of this, though, is to figure out will something happen or won't it happen? So we want to know will/won't happen. Okay. We're going to try to think fundamentally of what we would need to consider. Not these two things. Yeah, we can look at those and we can get that. But fundamentally, what are we talking about here when we're considering Gibbs free energy? So what properties should we consider? So if you think of the state functions we know, which ones do we have to really think of if we want to see if a system or a process will happen spontaneously? Entropy, definitely, because we spent forever talking about entropy, right? So we need an entropy. And what's the other thing we really need? So which of the laws of thermo gave us entropy? Yeah. What else do we need besides the second law? Yeah, we need the first law. And what property or state function do we really care about with the first law? Yep, internal energy. And Ellen, you said enthalpy, which is also true because enthalpy is related to internal energy, right? But there's certain conditions where we have to consider enthalpy over internal energy. Okay, So now we have our properties. Now let's think about what we need to happen with these properties to make something occur. What I want you to really think about is this equation a little bit over here. So, question. What are the optimal conditions to have a process occur spontaneously? So what do we want to happen with delta S? Increase, decrease, remain the same. Yeah, increase. We want more disorder. We want more randomness. That's what the universe wants. Give it what it wants. Okay, delta S needs to increase. What about delta U? I hate working with a little tiny piece of chalk. Delta U is what minus what? Well, there's Q plus W. I had that too integrated in your guys' minds because it's like almost muscle memory where you're saying it now. But what's another way to think about it? Yeah, U final minus U initial. Okay, what do we want to happen to delta U? Or another way to think about it, if we think about it in terms of a chemical reaction, it's what minus what? Yeah. So what do we want to happen to delta U? What was that? Yeah, we want it to decrease. We want it to give off energy. That's favorable. It's giving away energy. You're also increasing the entropy of the surroundings. So we want that to decrease. Okay. To show that this is true, we're going to go back to the Clausius inequality where we kind of found it. There's a way to derive it, but I really don't want to take the time in class to do that. Let's go back to this inequality. And it had to deal, sorry, it should be a big S. You guys remember that or remember seeing it when we were talking about the Carnot cycle? We like mentioned it for a second. Okay, what we want to do though is we want to transform this where we have 0 on one side. So let's subtract this thing. If we subtract, we don't have to change the direction of the sign, right? It's only when do we have to change the inequality sign? Yeah, divide or multiply by a negative number. We're not doing that, so we're okay. Okay. Now, we can consider this inequality in two ways. Two conditions. What do you think those conditions are? Constant what? Yep. Constant pressure. What's the other one? Yeah. Okay, I wrote them in that order for a reason. Which one do we want to talk about first? Yes, good. It's in the order I wanted. Last time I did that, they said constant pressure, and I said, no, we're doing volume. We want to do volume first because it's a bit easier to show what we're going to show. We can use this result and conquer that one in a minute too. Okay, so we're going to stare at this thing. We're going to consider it under constant V. All right. Okay. ds is not going to change, but what happens to the q? Q sub what? Let's go back to the first law. du is equal to what? Yeah, there we go. Muscle memory kicking in. All right, I got to shut the door. Professor Schneider's being too loud for me. Too excitable, that guy. All right. Yeah, because I'm no different. What are our conditions here? Okay, how is this first law equation going to change? Yep, because we're assuming only pressure volume work, so that's 0. What happens to Q sub, or what happens to dQ? Yeah, sub V. So how can we transform this equation? Yeah. That's good because we're out of Q. Serena, I saw your eyes dart. Oh, I erased it. I don't like a division under U. How many people like seeing division signs? Yeah, almost nobody does. That's another weird thing. I don't know why. How many people hate fractions? Okay, yeah, so like the majority of people in the room. I used to joke, so my wife was an elementary ed major, and I used to joke with her friends, I know how to tell you're an elementary ed major, and be like, how? What I would say is take 3/5 and add 1/2 to it and tell me the result, and they could never do it. Yep. Yeah. Yep. The way I do it, number lines. You mess with number lines and like little sheets, and you can show people that way. I showed my wife that. She was like, this is life-changing. And now she does it with every elementary teacher she trains. Okay. We don't like the t here. What are we going to do with it? Right. We're multiplying by t. We're not multiplying by negative t, though. So this inequality doesn't have to change. Let's multiply by t. What do we get? Okay. Before we do anything here, you don't have to really write this down. Have you seen anything that looks sort of close to this? Mainly this part. What's that look kind of close to? Yeah, looks close to Gibbs. What was it? Yep. It looks kind of close to that. Have you ever wondered why Gibbs needed to be negative to be spontaneous? Like, it's annoying, right? Positive is good most of the time, but with Gibbs, it had to be negative. This inequality is exactly why. So now, we're going to manipulate this a little bit because we're going to use it in a second. Now we want the du over to the other side. Okay. Bless you. Bless you. It's the most gentle sneeze I've heard. Like, all right. What we're going to do with that, we're going to consider a couple different scenarios. We're going to get some valuable information out of that. If du is equal to 0, let's look at our expression T ds, and we have it under constant situations. We're going to put those in subscripts here. We have volume. What else is constant if du is equal to 0? Yeah, the internal energy is equal to 0. What does that mean about ds? Or can I get an expression to isolate just ds? What can I do with that t? Yeah, divide. 0 divided by t? 0. So we've seen this before. For a process to be spontaneous, what is this saying? So what does the value of this thing have to be spontaneous? Yeah. It has to be greater than or equal to 0, like approaching 0. What does that sub v and sub u thing mean? Constant volume and constant internal energy. Where is the only time, whoops, you have constant internal energy? You have an ideal monoatomic, it's constant temperature. Okay, I want to be more general than that. We haven't gotten to an ideal monoatomic gas yet. U is constant. Where's another situation where du is constant or 0? Isolated system. This is saying entropy has to go up for an isolated system, right? This is the exact same thing. It's just restating the second law. Okay. Let's consider if ds is 0. What does our expression become then? What was that? Yep, 0. Greater than or equal to what? Not 0 in that case. So I'm sorry, we're stepping back and saying, yeah, just du. And what do we need subscripts? Yes. Where volume's not changing, what's that called? ISO what? Any ideas? C comes next. H. Yeah, it's isochoric. Nope. What about if entropy is remaining the same? Iso what? What's S stand for again? Entropy. So isoentropic, yep. Under those conditions. It seems weird because isoentropic means like there is no disorder change. But this is really just the thought idea. Okay. So really what we're saying what does this mean? What happens to the energy of the system? Yeah. The energy, the system must decrease to be spontaneous. Those are the things that you just told me had to happen to make a process favorable, right? You said entropy had to increase, and then you said that energy, you had to lose energy, or the products had to be lower in energy than the reactants to be the most favorable, right? That's inherently what's going on here. The weird thing about PChem is you guys have way more intuition than the numbers, but as soon as numbers and equations go up, you get less confident in your intuition. But it's all built upon this stuff.